Every winter, the same frustration returns. The heating bill rises, the furnace runs all night, and the house still feels cold by morning. In Newfoundland, a man named Eddie Roberts decided to challenge that cycle with a solution that cost less than $50. Instead of relying on expensive equipment, he gathered 256 used aluminum beer cans, painted them flat black, arranged them in vertical columns inside a wooden frame, sealed the front with glass, and installed the unit on a south-facing wall. Then he measured the results. On a cold winter morning, the air entering the collector was 60 degrees Fahrenheit, but the air coming out reached 218.5 degrees. No electricity, no motor, no complicated machinery, and no monthly bill. It sounds unbelievable at first, but the real surprise is not that it worked. The surprise is that so few people know about it. Eddie Roberts was not alone. In the snow belt near Lake Michigan, another builder named Guy Sperry created his own solar air heater using 240 aluminum cans, a sheet of glazing steel backing, and an aluminum frame. He built it himself over a single weekend. Then winter arrived. On one of the coldest days of the year, with the outside temperature near 4 degrees Fahrenheit and icy wind sweeping across the lake, Sperry checked the temperature inside the collector. It had climbed to 172 degrees. His furnace did not run once that day, yet his small house stayed warm. This was not luck, and it was not fantasy. It was sunlight, recycled metal, and physics working together in plain sight. You can ignore a strange invention, but you cannot argue with measured heat. That is where this investigation truly begins today. So how can a simple box filled with painted aluminum cans produce that much heat? The answer is thermosiphon physics, a natural convection cycle that works without fans or electricity. Sunlight passes through the clear front glazing and strikes the black painted aluminum surface inside. Because black surfaces absorb radiation efficiently, the cans heat up quickly. Aluminum also transfers heat extremely fast, much faster than many other common building materials, so the warmth spreads through the can columns almost immediately. As the air inside those columns heats up, it becomes lighter and begins to rise. That rising hot air exits through the top vent and flows into the room. At the same time, cooler and denser air from inside the house is drawn into the lower vent to replace it. Then the cycle repeats again and again as long as sunlight remains strong. In other words, the sun creates a continuous loop of moving warm air, turning discarded cans into a silent heater powered entirely by daylight. Real-world tests make this system even more convincing because the results were not limited to one person or one location. In Oklahoma, a builder documented a homemade solar heater built with salvaged materials for about $70. At an outdoor temperature of 40 degrees Fahrenheit, the unit delivered air at around 150 degrees. When the outside temperature rose to 55 degrees, the output reached 180 degrees. Those numbers are impressive for a device with no moving parts and almost no operating cost. Still, honesty matters here. This is not a magical replacement for a furnace, and serious builders do not pretend otherwise. On cloudy days, the output can fall dramatically, and under heavy overcast skies it may drop close to zero. But that limitation does not make the system useless. It makes it realistic. A retired Boeing engineer named Gary Rea found that even after accounting for weather, his collector could still produce free heat equal to burning about 2 gallons of propane on a sunny day, paying for itself in less than a year. What makes this story even more fascinating is that none of these ideas are truly new. Humans have understood the basic logic of solar heating for centuries, then repeatedly allowed it to fade from common use. In 1767, Swiss scientist Horace Benedict de Saussure built a simple insulated wooden box with a glass lid and a black interior. He called it a hot box. Under direct sunlight, the temperature inside rose to more than 230 degrees Fahrenheit, proving that solar radiation could create intense heat even when the surrounding air was cold. But the principle goes back even further. In ancient Greece, entire cities were planned so homes could face south and capture the winter sun. Centuries later, The ancestral pueblos of Mesa Verde used cliff geometry, thick stone walls, and seasonal sun angles to hold warmth in winter and reduce heat in summer. These were not primitive accidents. They were intelligent designs based on careful observation of sunlight shade and thermal mass over time. By the 20th century, solar heating was no longer just an ancient architectural instinct. It had become a serious scientific pursuit. In 1945, George Love built one of the first modern solar air heating systems at his home in Boulder, Colorado, showing that captured sunlight could be directed into a living space in a controlled and practical way. Only a few years later, Maria Telkes pushed the idea even further. Working with architect Eleanor Raymond, she helped create the Dover Sun House in Massachusetts, a home designed to be heated entirely by solar energy. The system used flat plate collectors and thermal storage materials to hold warmth after sunset. Remarkably, it worked through multiple winters. Telkes was not an amateur experimenter, but a respected scientist with numerous patents and a record of life-saving inventions. Her work proved that solar heat was not a fantasy, not a niche curiosity, and not a symbolic gesture. It was a functioning technology capable of keeping real homes warm. The pattern then is not discovery. Discovery has happened again and again. The real pattern is abandonment. Each time solar heating proves itself, it gains attention for a moment, especially during periods of fuel scarcity or economic pressure. Then cheap, conventional energy returns, public interest fades, manufacturers disappear, and the knowledge is pushed back to the margins. That is why this story is larger than one homemade heater built from aluminum cans. The technology works. The history is real. The evidence stretches from ancient cities to 20th century laboratories to modern garages and workshops. What keeps these systems from spreading is not a failure of physics, but a failure of priorities. When a technology offers comfort without recurring fuel purchases, it does not fit neatly into industries built around monthly dependent centralized control and billable consumption. That conflict becomes visible the moment a homemade heating system meets the modern regulatory world. In many places, any device considered heating equipment must be listed by a nationally recognized testing laboratory. That usually means formal certification through an organization such as UL or another approved body. On paper, this sounds reasonable. In practice, it creates a barrier that most small builders can never cross. A solar air heater made from recycled cans may cost only a few $100s in materials, yet certification can cost tens of thousands more, far beyond the value of the product itself. The problem does not end there. Local codes may require permits for wall penetrations, inspections for installation, and insurance policies may refuse coverage for any non-listed equipment. None of this looks like an outright ban, but the result can feel almost identical. The system is technically possible, physically safe when built correctly, and economically attractive, yet still pushed outside the legal and financial framework of ordinary housing. This is why so many practical solar heating ideas remain in garages, workshops, and internet forums. The issue is not simply whether they work, the issue is whether the system was ever designed to make room for low-cost self-built solutions. The obstacle goes beyond certification. In many communities, homeowners associations and local design rules can restrict even conventional solar installations, let alone experimental or self-built systems. That means a homeowner may have the technical ability to capture free heat from sunlight, yet still be blocked by paperwork, neighborhood covenants, or property rules written with appearance in mind rather than resilience or efficiency, and the soda can heater is only one example. Trombe walls, rocket mass heaters, earthships, and other low-cost energy-saving designs often face the same challenge. They are practical, proven in specific settings, and often remarkably efficient, yet they do not fit comfortably inside a regulatory culture built for standardized commercial products. A factory-made unit arrives with labels, manuals, and approved testing. A site-built solution arrives with craftsmanship, local adaptation, and evidence from the field. The first fits the system immediately. The second must fight for permission. That imbalance has shaped which ideas become normal and which are dismissed as fringe, even when the so-called fringe technologies can reduce fuel use, increase independence, and help ordinary households lower their energy burden. Politics also shaped the rise and decline of solar heating in the modern era. During the energy crisis of the 1970s, interest in solar technology surged as fuel prices became unstable and national energy security turned into a public concern. The United States began investing more seriously in research, and solar energy briefly looked like part of the future. President Jimmy Carter even placed solar panels on the White House, turning them into a visible symbol of a different energy direction. But symbols can be reversed. In the 1980s, federal support was cut sharply, research budgets were reduced, and much of that early momentum collapsed. The removal of the White House panels under President Ronald Reagan became more than a practical decision. It represented a broader political retreat from renewable energy at the national level. Once again, the technology itself had not failed. What changed was the willingness of institutions to support it. What makes this even clearer is that other places chose a different path and achieved very different results. In Canada, commercial solar air heaters, built from recycled aluminum cans, showed that the concept could move beyond hobby projects into real products. In Denmark, solar district heating expanded on a massive scale, proving that even a country with limited sunshine could use solar thermal effectively when policy supported it. The difference was never just the amount of sunlight available. It was the willingness to treat solar heat as legitimate infrastructure. Larger systems such as solar wall were adopted in factories, military facilities, and industrial buildings across many countries, showing that solar air heating could serve both small homes and major institutions. At the same time, students and independent builders continued testing low-cost versions, made from scrap materials, often producing meaningful amounts of heat with very small budgets. All of this points to the same conclusion: the barrier is not the sun, the materials, or the physics. The barrier is whether a society chooses to encourage practical energy independence or quietly leave it on the margins. So the question is not whether a box of painted aluminum cans can make useful heat. It can, and that has been demonstrated in garages, workshops, laboratories, and full-sized homes for generations. The real question is why a family can fall behind on energy bills while solutions built from scrap sunlight and basic physics remain almost invisible. A simple solar air heater will not solve every winter problem, and it will not replace every furnace, but it can reduce fuel use, lower costs, and give ordinary people one small measure of control over their own survival. That matters, especially in a world where energy debt keeps rising, while free sunlight still arrives every morning without a contract, a meter, or a subscription fee. 200 discarded cans, a dark surface, a sheet of glazing, and one weekend of work may never fit the logic of a centralized industry. But they fit the logic of self-reliance. Build one carefully, test it honestly, document the results. Then show someone else, because once people remember that heat can come from sunlight and waste, they may start questioning how many other forgotten systems were buried simply because they made dependence less profitable.